In the previous episodes, we explored how k-nearest neighbors works and how to evaluate models using techniques like validation sets, RMSE, and cross-validation. In this video, we're going to look at a completely different approach to regression: decision trees. Instead of predicting values by averaging nearby points like k and n, decision trees work by dividing the input space into regions using simple rules. Each region is assigned a constant prediction, usually the average of the training data that falls inside that region. These rules can be organized into a structure called a binary tree. Every internal node represents a decision or split. Every endpoint of a branch is called a leaf node, and the lines connecting them are the branches. The tree is binary because each decision divides the data into exactly two parts. To build a tree, we need to determine both the structure of the tree and the prediction the model assigns to each leaf. If we already knew the final tree structure, computing the predictions would be easy. We would simply take the training samples that land in each leaf and average their outputs. But the real challenge is figuring out the shape of the tree itself. To learn this shape, decision tree algorithms use a greedy procedure called recursive binary splitting. The term recursive means that the splits are determined one after another, starting from the top of the tree, which we call the root, and working downward. At each step, the algorithm picks the split that gives the best immediate improvement in explaining the training data. It doesn't try to plan ahead or consider the entire future shape of the tree. It simply makes the best decision it can at each stage. If we continue splitting until each leaf contains exactly one training point, the resulting model will perfectly reproduce the training data. This is similar to k and n when k equals 1. But just like k and n with k equals 1, a fully grown tree tends to overfit the training data and becomes extremely sensitive to noise. To mitigate this, we usually stop the tree from growing too deep by choosing a maximum depth, limiting the number of leaf nodes, or specifying a minimum number of samples required to form a leaf. Tree depth is especially important because it controls how flexible the model is. A very deep tree captures every wiggle in the data, even when those wiggles are just noise. A shallow tree, on the other hand, produces smoother predictions by averaging over more points. This is the same trade-off we saw in k and n between choosing a small value of k, which overfits, and a large value of k, which oversmooths. If you want to experiment with tree depth interactively, I've included a link to the notebook in the description. Now that we understand the idea behind decision trees, let's work with the data set and build a model. We start by importing the data using pandas and loading the same car stopping distance dataset we used earlier. After previewing the top rows with the head method, we import the decision tree regressor from scikit-learn. We define our input variable, which is the vehicle speed, and our target variable, which is the stopping distance. Then we fit the decision tree model on this data. If we use the fitted model to predict the stopping distance for a vehicle traveling at 33.5 miles per hour, the model returns about 106.93 feet. The actual stopping distance is 115.32 feet, so the prediction is quite far off. Checking the depth of this tree, we can see that it grew to a depth of 8. In the previous episode, we learned how to use cross-validation and grid search to choose the best version of a model from a collection of models with different hyperparameters. We'll do the same thing here. We use grid search CV to test decision trees with maximum depths ranging from 1 to 11 and evaluate each one using 50-fold cross-validation. We choose the model with the smallest validation RMSE. The best tree has a maximum depth of 5. And its mean validation error is about 14.11 feet. This is noticeably larger than what we achieved using k and n. When we use this best model to predict the stopping distance at 33.5 miles per hour, we get the same prediction as before, 106.93 feet. If we apply the error margin of plus or minus 14.11 feet, the model's prediction falls within the range 92.82 to 121.04 feet. The actual stopping distance 115.32 feet, does fall inside this interval. But we can clearly see that the tree does not capture the variation in the data as well as we would like. With this, we have a good understanding of how decision trees work for regression and how their performance compares to KNN on this dataset. In the next video, we'll investigate linear regression, a classic model in machine learning, and see whether it provides a better fit for this car stopping distance problem.